Good day to you all. I'm very happy to be here again. We shall be discussing physics as well. I am S.Adebayo, and today we shall be discussing about the elastic properties of solids. Now, the content and the objectives that you want to achieve today is the first one. We want to talk about elasticity, talk about the Hooke's law, the stress and the strain, tensile stress or tensile strain, Young modulus, and the work done in stretching an elastic material. When a material is subjected to a force, whenever you try to subject any material to a force, the material deforms or change shape. You have ever seen when you try to pull out maybe a cloth, or you pull out a kind of material that is elastic, you try to deform it or try to stretch it beyond, apply the force, you will see that there will be a change of shape. So the deformation can take place in any of the following. So what I said there is that any material that is subjected to a particular force of very high magnitude will tend to deform. When I say deform, the shape changes automatically. And whenever you try to apply that force, it can cause three things. First one, change in length. If you hold an elastic material now, try to expand it, you see that it become more longer than what you have before. So change in length, that is the force. That force is called a tensile force. Second one is change in surface area or volume. Change in surface area, that is the area, we call it bulk force. And we have change in shape. The shape will also be changed. These are the three changes we have whenever a very high force is applied to a body. And however, the deforming force is removed. When you remove the force, the materials will return back. When you remove the force, when you take a cloth and you expand the cloth, it expands because when you remove that force, it comes back to the original position. So when the deforming force is removed, so materials will return to their original shape or size, while other materials will not. So that any material that returns to the original dimension or shape or size after you remove the force, deforming force has been removed, that material is said to be elastic. Look at what you have there. And when you have elastic, most of you have seen elastic material. There are some elastics that they use in cloth, and this white one, when you try to expand it, when you try to elongate it, it elongates. When you release it, it comes back to the original position. That is elastic material. But when there's some material, by the time you elongate them, they elongate. By the time you remove the force, you stop elongating them, they will stay like that. They will not come back to the original position. Such a material is said to be a non-elastic material. So any material that returns to original dimension or shape after the deforming force has been removed, they are called elastic materials. So the ability of a material to return to its original shape or size after being distorted by an external force is called elasticity. So elasticity is the ability of a material to return to the original shape or size after the deforming force has been removed. That's just simple definition of elasticity. The ability of a material to return to its original shape or size after a deforming force has been removed. Now let's look at the Hooke's law. Try to hold the spring at both ends and pull in opposite direction. Gradually increasing the force, we will notice that the more the force applied, the greater the increase in the length of the spring. I think I told you before, the spring is also elastic in nature. By the time you try to put your two hands at the ends of the spring, try to apply the force, it goes. By the time you remove it, goes back. So the length of the length of the spring increases as you pull out. Now, how does Hooke's law say that? Hooke's is a scientist that worked on the elasticity. He was one that discovered that material are elastic, they obey what we call a particular law, which is what we are trying to say. So the material, the Hooke's law, Hooke's law states that the external force applied to an elastic material is directly proportional to the elastic limit of the material if the elastic limit is not exceeded. It's proportional to the extension of the material if the elastic limit is not exceeded. He said that the force applied is directly proportional to the extension. That is, the more you apply the force, the more the extension. That's what the Hooke's law is talking about. Hooke's law states that the force applied to an elastic material is directly proportional to the extension, provided the elastic limit is not exceeded. Let me tell you one thing about elastic limit. Any elastic material has elastic limit. Any elastic material has elastic limit. For example, if you take an elastic material, this common white one that they are used in our clothing, try to expand it, elongate it, it elongates. Release it, it comes back. Elongate it the more, elongate, it elongates. Release it, it comes back. Elongate the more. When you get to a time when you elongate and you release it, it will not come back, it will stay. That means that material have reached what we call elastic limit. That point, any material that say comes back to the original position after you release the force, it has not yet reached the elastic limit. It's still in the elastic region. That material is still in the elastic region. Most of us, when we wear some trousers or some boxers, we say it is slack. Slack means that it is no longer coming back. It's no longer compressing. It has stayed. That means it has reached what we call elastic limit. Whenever any material is not coming back to the original position, that material has reached elastic limit. So once the material is still coming back to the original position after you remove the force, that material has not yet reached elastic limit or is still in the elastic region. So Hooke's law now said that provided the elastic limit is not exceeded, you have not gotten to that range, the force will be proportional to the extension. Whenever the elastic limit is exceeded, the force will no longer be proportional to the extension again. Because when you apply the force, it will not extend the way you want. So the more the force, the more the extension, provided the elasticity is not exceeded. And that's exactly what the Hooke's law is talking about. So in that vein, it now says force, when you apply constant, equals to Ke. Force equals to Ke. So we can now say our K equals to the force over the extension. Our K equals to the force over extension. So we can also say, according to that, I can say my F1 over E1 equals to, that's a constant, F2 over E2 equals to F3 over E3 in that manner. That's exactly what we are talking about. So that's exactly what Hooke's law says. You must be able to state Hooke's law. They are common wide pass question and echo. State Hooke's law, and you also solve some problems on that. And let's look at issues about Hooke's law. Some problems. First one, a force of 50 Newton. That's a force, and that's what you are giving here. Extend a material. Look at the material. Extension 0.05 meters. Calculate the force constant. The force constant is what we call K. You know, I told you when we have the Hooke's law saying this, we now have F equals to Ke, and this is exactly what we call the force constant. So our K, which is the force constant, our K equals to force over the extension. And that's exactly what we are having here. So, and we are given the force in the question to be 50 and extension is 0.05. So our K becomes here 1000 Newton. I forgot to tell you that the unit of the constant K here is Newton per meter. Don't forget it is force over extension, and force is in Newton, extension is in meter. So the unit of K constant, the constant is Newton per meter. Now let's look at another example. The length of a spring or is 16 centimeter when a load of 5 meters is attached to it. When the load attached to the spring is 20 meters, the length is 19. Calculate the force constant. You can see they give us two conditions here. In the first one, they attach a load of 16, and a spring is 16 length and the load is 5. Second one, the spring is 19 centimeter when the load is 20. Now in the first case, let's say that the original length of the spring when they have not applied the force, let's call it L0. So that means the extension in the first case will be, they say it's extended by 16. Its length, the length of a spring is 16 when a load. So before the load, let's call it L0. When a load is applied, after they must have applied that force, you don't forget that load there means force. It is 16. So when that means before the load, it was something. So that's why we call it L naught, the original. So the first one, E1, is 16 minus L naught. Don't forget 16, that's the final length minus the original length. While the second one is that one is extended by 19, that will be 19 minus L1. And the first is this, the second force is this. And don't forget in the Hooke's law, we were able to say that the first F1 over extension equals to force 2 over extension. That is when we say K equals to F over E. So that's exactly, if you look at back at your slide, that's exactly what I talk about. So we now apply that formula. We have force 1 to be 5, force 2 to be 20. So substituting that into the equation, we have 5 over 16 minus, we have this 5 over 16 minus L naught equals to 20 over 90 minus L naught. That is F1 over E1 plus F2 over equals to F2 over E2. So by the time we substitute and you cross multiply here, you have this one here. When you cross multiply, that will be 5 by 19 plus 5 by LO minus LO equals to 20 by 16. That is what we have to be 320. And we have 20 by minus LO. That's what we have, minus 20 LO. So then you make LO the subject to formula L naught. Then we have this. And we have our L naught to be 15 centimeters. I hope that is very clear enough anyway. Okay, the second question, I think we have to find the original length of the spring. Don't forget, original length is the L naught. And don't forget, in this equation now we are able to get L naught. Now the first constant K is what we want to get now. The first constant K. So we have known that we can pick any of the equation that we solved, that we used here. The equation. What is the equation? The one I used here is K, the first F, we say K equals to F over E. It can be F1, F2, it can be F3. And we have the force. In the first case, they say it's extended by 5 Newton, and when they apply 5 Newton load, it's extended by 16. So extension is 16 minus L naught. That is the in first case. And don't forget, we have gotten L naught in our previous question. So we just have to substitute the L naught. You can use the other second method too. That is when it is extended by 19. You can use that second formula too. It will still be the same thing. So you get 15 here and you get your K to be 5 Newton per centimeter. Now, the experiment to verify Hooke's law. This is a typical experiment to verify Hooke's law. Do we have helical spring? We have set of standard mass. This is a kind of second lab experiment we are going to be performing when the school resumes. Last week I gave you an experiment too that said we will perform it when we resume. So we are going to be performing this experiment because this experiment is what we call basic Hooke's law experiment. And what does it say? Well, look at the apparatus here. The apparatus, this is the apparatus. The tripods, we have the Peter stand, we have the spring, we have the set of masses here, we have the ruler. So before you look at it, if you follow this protocol, because this is exactly what we will be doing in mostly practical, so I would not want to waste much of the time here. But what I know is that before this mass is attached to this spring, we take a measurement. You just put the string there, take the measurement. By the time you apply the mass, the spring draw down. That is another measurement, which is the L. So extension now becomes L minus L naught. It's as if you have a spring. Before you apply a mass or set of masses on that, excuse me, set of masses on that spring. Whatever you apply, before you apply the set of mass, there is spring have a length. You measure it. That is L naught. By the time you now apply the masses there, there is extension. So you now take that one to be L or L1. So extension becomes L minus N. If you now plot the load or the force, if you plot the load or the force against the extension in this apparatus setup, you're going to get what we have, the graph of what we have there. We're going to talk about this one more when you get to the laboratory. Then you see it your face. This is a practical, and we can be explaining practical by by saying. It's better done in the lab. So when we get to the lab, we do more of this. Now, the elastic limit. I was explaining something to you last time. I said whenever a material is still in the elastic limit, then the material will still be elastic. Sorry, whenever a material has not reached the elastic limit, the material will still be elastic. But whenever the material reaches the elastic limit or above, the material will not be elastic. And what do we say a material is elastic? When it can come back or go back to the original position after we have removed the force. So elastic limit can be defined as a limit of a force beyond which the deformed material does not return to its original dimension. When the force is removed, you can say the limit, you can say it is a limit of force beyond when the deformed material does not return to the original dimension when the force is removed. So if the external force is increased beyond the elastic limit, the force extension graph obtained is as shown. Look at this. Until this stage, the elastic limit is still there. It's still onto that stage. Because I see the force, whenever the force extension graph is still linear. Elastic limit has not been exceeded. Excuse me. It's still linear like this. But by the time you see a curve, then it means the elastic limit is longer. So in the force extension graph, you have the elastic limit to around P in this graph there. The elastic limit is around P. It's still maintained to around P. Excuse me. The elastic limit is still around P in that diagram. You see, elastic limit is still up to that area. Excuse me. Elastic limit is still to this because it's still linear. That is from O to P. We call it proportionality region because the force is directly proportional to the extension during that range. But from P above, the force is no longer directly proportional. Don't forget, during the elastic limit in the elastic region, force will still be directional to the extension because the more the force, the more the extension during the time from 0 to the P here. But beyond the elastic limit, the force will no longer be proportional to the to the E. It gets to the E. Look at it at E. It gets to the E. So it's as E that starts misbehaving. So proportionality limit is P, and the elastic region is OE. Look at that. The elastic limit is E. The yield point is Y. The plastic region is EB. That is plastic region. B is breaking point. Now we are going to be explaining this one after the other. I will explain this. Now let me explain plastic region because it's one of the. When we say plastic region, beyond the elastic limit, the material becomes plastic in nature. Plastic. You know, when I try to expand plastic, even if it expands, it does not contract back when I remove the force. So any point after the elastic limit, the material under consideration becomes plastic. We call it plastic. So that's why we have E to B is a plastic region. From O to E is an elastic region because during the time O to E, any force we apply, we still have it be directly proportional to the extension in that. Now when we say yield point, the yield point can be defined as a point beyond the elastic limit in which the elastic material has yielded all its elasticity permanently and has become plastic. You can see. Whenever that point beyond elastic limit in which the elastic material has yielded, it's as if you have a material that is elastic. You elongate that material, it comes back. You elongate the more. You apply it, it comes back. You remove it, it comes back. You elongate the material, the more you still remove the force, it comes back. You elongate the material, the more you leave it, it does not come back. You leave it still, it does not come back. It's not coming back again. You can say that time it is yielding. You still elongate the material, the more you leave it, it does not come back. It's expanding, it's increasing, there is increasing in length. It is that point, it is yielding. If the yielding point get to a particular point that you have been elongating that material, what happens? It will break. So that's when you now get to the breaking point. The time that material is yielding that force is yielding. You are trying to expand and it's not coming back to the original position. It's still increasing. It is increases. It does not come back to it is yielding. So any points beyond the elastic limit, when the material has yielded all its elastic permanently and has become plastic. And the breaking point is the point corresponding to the maximum weight the elastic material can withstand without breaking. So when you try to get to a particular state where you have been expanding, the material is yielding. If care is not taken, if you still expand better, what happens to the material? It will break, it will fracture. That point at which that material does that is what we call breaking point. Let's quickly look at the tensile stress, strain, Young modulus. A tensile stress can be defined, the stress, as a ratio of the tensile force to the cross-sectional area of the material. So tensile stress is force over area. Tensile stress is force over area. So when you are asked to find the stress of a material, just get the force of that material over the area of the material. The tensile strain is defined as the extension of our original length. Extension produced to the original length. So when you have extension E over the original length, because before a material extend, there will be an original length. There will be a length at which that material was originally before you start extending. So the strain is the extension over original length. The Young modulus is defined as the ratio of the tensile stress to the tensile strain. So later now, the Young modulus is stress over strain. The Young modulus is stress over strain. And don't forget that we said our stress is F over A and our strain is extension over L naught. So by the time you now write this for F over A divided by E over F naught, you are going to get this equation. The sign of your modulus is like Y. That's what I'm saying. So this exactly, I hope you understand this, because this exactly will be F over A divided, that is stress, divided by, stress divided by strain. That is, strain is the extension over length. So by the time you now cross multiply, so you invert this one, you get this one to be, you get to be this one multiplied by, it now becomes N naught over extension. So that's why you now get this out. F times N naught give you Fn naught over AE. So the Young modulus is then FL naught over AE, in which the E is the L minus, don't forget extension, that's extension, original length subtracted from the final length. And don't forget that area is pi d square over 4, because whenever we have this is more or less that we have a spherical or circular material, pi d square over 4, and this is derived from pi r square. When you substitute a radius is diameter over 2. When you put diameter over 2 as a radius in pi r square, what you get is pi d square over 4. So don't forget that area is pi d square over 4 and the extension is L minus N naught. Let's look at work examples on this. A material of wire 1.2 and cross sectional of 2.0 tensors per minus 7 is stretched by a force. You can see that's a force F, and they gave us cross sectional area. Don't forget cross sectional area, that is A, and this is the length, that is L naught, the original length. So we say how to find the tensile stress. What is tensile stress? Stress equals to force over area, and the force is 50. What's the area? 2,000, and that's exactly what it is. So a stress, this is a force is in Newton, and area is meter squared. So that's why the unit of stress is Newton per meter squared, or Newton meter raised to power minus 2. Don't forget that the stress is measured in Newton per meter squared. The second one, they say we should find the strain. Don't forget the strain. In the question we are given that the force constant, look at the force constant of the material is 6,000. That is a K. You are given a K to be 6,000. K to be 6,000. Now, a strain. The strain is extension over original length. And we are given K to be 6,000. We are given the force to be 50. So we can get the extension there. So that is from the relation that says K equals to F over E. That is force Hooke's law. Hooke's law was the one that said that. Hooke's law said that force is directly proportional to E and F equals to KE and K equals to F over E. So then we get our E out because we need to know the extension before you can find the strain. So our extension is this. So we now use the strain equals to extension of our original length. Original length has been given to be 1.2 in the something. So we have the strain to be this. Don't forget, a strain has no unit. Why? It is a unit. It is the ratio of two lengths. Extension is a length. The original length is a length. So length over length is still it will be still the same. It will cancel out. So a strain has no unit, but stress has Newton per meter square as a unit. The last one, which is the Young modulus. Young modulus is the force stress over strain. We got the stress in our last something to be 2 times by 2.5 times by 8, and our strain is 0.006917. So the Young modulus is then the division of the two. I will get the Young modulus equals to that over Newton meter square. Don't forget, both the Young modulus and the stress has the same unit because and the stress they have the same unit. The Young modulus is a Newton per meter squared. The same thing is stress, Newton per meter squared. Why? If Young modulus is stress over strain, strain has no unit. So that means Young modulus will take the unit of strength. So another example here. Let's look at the work done in an elastic material. Work done under proportional religion. The work done of an elastic material is given by this three equation. W equals to 1 over 2 Fe, or W equals to 1 over 2 Ke squared. That's when we are given constant and extension. This is used. When we are given force and extension, this is used. If you are given force and constants, this is used. These are the three formulas to get, because whenever a force causes a distance, don't forget, a work done is whenever a force causes a distance to move in the direction of force. So whenever there is a force applied in the elastic material and there is a particular distance or extension move, then a work is done. So the calculation of the work done is done by the three equations we have there. An example of this: calculate the work done required to stretch a wire from E to F. Look at this, from E to F. The wire was originally here and now it is here. And don't forget, let's look at the work done. Don't forget, they were given more or less force and extension here. And don't forget that the formula here, the work done according to work is half Fe. But the first one, this is the first case. In this first case, we have our force to be 0.1. We have our force to be 0.1, and we have the extension to be 0.05. That's the first case. And the second one, we have our force to be 0.2 Newton, and we have our extension to be 0.1. So we want to now look at difference between these two. So the first one is that half Ke for the first one. What is the final one? The final minus half Ke for the initial. And don't forget, the final is this one and the initial is this one. So that's exactly, so we have Ke. That's exactly what you have there. So we have 0.1 plus 0.2. That is the K. And the E is the 0.1 minus 0.005. So I want you to look at the examples very well, critically. That's exactly what we have there. And another example is this. We are given the force constant and the force. And we use the third formula, which says that W equals to half F square over K. Just directly substitute that, you get your work done to be that. These are work examples or questions I want you to work upon. Try and work them inside your assignment books. I shall pick you up very soon. Work them and let me know if you have any issue with everything I've just explained. Thank you very much. Greetings to everybody there, and make sure you are staying safe. Good day, everybody.